Hello, my name is Brian Ho, and I'm a PhD student in the Personal Robotics Lab at the University of Washington. In this talk, I'll be introducing a new formalism for anytime motion planning, as well as an algorithm that uses learned structure about the world to quickly discover and refine paths. In motion planning, finding the shortest collision-free path can be computationally expensive. This has real consequences in many robotics applications. So when these systems have hard time budgets, they're often willing to accept any collision-free or feasible path. This can be computed in less time, but the solution usually has higher cost. In practice, what winds up happening is that the system finds a feasible path quickly, then uses the remainder of its time budget to progressively find better ones. This is what anytime motion planning is all about. The literature mainly considers the question of asymptotic optimality. Will the pink curve converge to the shortest path? This is an important property, but realistic time constraints mean that we can't run these algorithms until convergence. So as practitioners, we want theory that helps us decide which anytime algorithm to deploy. For example, we might want to know, how quickly does the algorithm discover an initial feasible path? Or, given a time budget, how suboptimal will the path be? This work formalizes some of these questions. Anytime planning is inherently concerned with computation time, and collision checking is a bottleneck for many of these algorithms. In this plot, we see one example where over time the computation becomes dominated by edge collision checking. This has led to the development of lazy algorithms that explicitly decide when to evaluate edges for collisions. In this example, a lazy algorithm initially proposes the blue path to the goal. That path is collision checked and rejected, so the algorithm finds another route. Prior work has shown that predicting which edges will be in collision helps a lazy algorithm quickly identify feasible paths. In this work, we'll be modeling this as a posterior distribution, where we condition on the results from previous collision checks. Our key insight in this work is to formalize anytime search as an instance of Bayesian reinforcement learning. This novel formulation establishes equivalences between reinforcement learning and lazy motion planning problems considered in previous work. We focused on the fixed graph setting, where edges are lazily collision checked so their statuses are initially unknown. We defined the anytime objective to be the cumulative length of discovered paths as edges are evaluated. This penalizes an anytime algorithm for not finding a feasible path quickly, or taking too long to refine a suboptimal path. In the Bayesian anytime setting, an algorithm has a little more information. It knows the distribution over the binary edge collision statuses, where phi is a world vector that bundles all the edge statuses together. On the right, you can see some instantiations of the world and the resulting prior. The Bayesian objective is the expectation of the anytime objective over this distribution of worlds. A Bayesian planning algorithm can use a history of edge evaluations to compute the probability of collision for the remaining unevaluated edges. In the paper, we model anytime search as a deterministic Markov decision process. Then, the Bayesian anytime planning problem is actually equivalent to the episodic Bayesian RL setting considered in prior work, where an algorithm infers the unknown MDP over repeated episodes of interaction. Their objective is called Bayesian regret, or expected regret. It basically asks, if my kth policy, mu k, had been the optimal policy, mu star, how much better would I have done? In expectation, how much more value would that optimal policy have accumulated? Our definition of the anytime search MDP translates that into, in expectation, how much longer was the kth path than the optimal path? This recovers the expected cumulative length of discovered paths offset by a constant. In other words, minimizing Bayesian regret is equivalent to minimizing the Bayesian anytime planning objective. Intuitively, a low Bayesian regret corresponds to evaluating edges that not only lead to shorter paths, but also drive down uncertainty over time. This connection allows us to import Bayesian RL algorithms to solve the Bayesian anytime planning problem. We introduce a new search framework that encompasses several existing algorithms in the literature. The proposer uses the collision posterior to propose a new path to the goal. The validator chooses edges along the path to collision check, and the results are incorporated into the posterior update. If the entire path is collision-free, it's saved as the current shortest path, and can be returned if the time budget runs out. Our algorithm, posterior sampling for motion planning, chooses the proposer to guarantee strong anytime performance. The key idea is intuitive. Propose paths according to the probability that they are optimal. This comes from the multi-arm bandit literature, where it's also known as Thompson sampling. This strategy enjoys strong empirical performance, but regret bounds weren't known until quite recently. PSMP is the first anytime motion planning algorithm with Bayesian regret bounds. We adapt the Bayesian RL analysis for the special case of a deterministic MDP, resulting in a tighter sublinear regret bound that matches known lower bounds. Unlike other Bayesian search methods, PSMP is quite computationally efficient. It only requires solving a single shortest path problem per iteration. It uses the posterior to sample a collision status for every edge in the graph, either free or in a collision, then solves for the shortest path on the resulting graph, which is visualized here in blue. The proposed path is collision-free, so the algorithm updates its current shortest path in yellow. The results of the collision checking update the posterior, and the algorithm repeats. As PSMP gains more information, the posterior concentrates around the true world, and PSMP proposes shorter paths. In our experiments, we've considered two possible posterior models. On the left, we compute collision probabilities on the configuration level using a nearest neighbor model. The intuition is that nearby configurations are likely to have the same collision status. This is a very mild assumption, which can be used in new environments where the world structure is unknown. However, we may know that the world will be chosen uniformly from a finite set of possible worlds. With this stronger assumption about the world structure, we can filter out worlds that are inconsistent with previously collision-checked edges. Then, the remaining worlds can be used to compute edge collision probabilities. We evaluate the anytime performance of PSMP on 2- and 7-dimensional motion planning datasets. The Baxter manipulator environments were generated by randomly perturbing objects from an initial cluttered environment. We compare PSMP with two other algorithms on this environment seen in the top right corner. The LazySP baseline is a shortest path algorithm that minimizes the edges evaluated before discovering the shortest path. Since it's not an anytime algorithm, it only produces one solution, taking about 4,700 collision checks. The Pareto Optimal Motion Planner, or POMP, is an anytime algorithm that balances the two criteria of path length and feasibility. Initially, it focuses entirely on feasibility to quickly discover a collision-free path, then gradually shifts the balance towards path length. The top plot shows the length of the current shortest path over time, demonstrating that POMP quickly finds a feasible path, but is slow to discover shorter ones. Using the same finite set posterior as POMP, PSMP finds a shorter feasible path in fewer collision checks, and quickly converges to the optimal path. We can overlay the curves from the previous slide to understand each algorithm's anytime performance across many different environments with different shortest paths. For PSMP, using the informative finite set posterior converges to the optimal path in fewer collision checks than when using the weaker nearest neighbor posterior. On the other hand, POMP's strategy of prioritizing paths that are likely feasible actually results in worse performance when using the more informative posterior. On the right, we visualize the collision checking budget versus the percentage of planning problems where that budget is sufficient to discover a feasible path. PSMP with a finite set posterior requires the fewest collision checks to solve all the problems, while LazySP requires more collision checks than all 4 anytime algorithms. The story is a little different in these simple maze-like environments on the bottom right. The right plot shows that PSMP with the nearest neighbor posterior can actually require more collision checks to discover any path than LazySP requires to discover the optimal path. We believe that this is because PSMP's anytime objective implicitly assumes the existence of multiple feasible paths. Posterior sampling can explore paths quickly, but it can only do so much if the posterior is slow to shrink the set of possible paths. As a result, relying on sampling to discover one of the few feasible paths may be undesirable with a less informative posterior. In this scenario, the finite set posterior quickly eliminates all other paths, helping PSMP discover the optimal path. In the Baxter environments, we additionally compare with the common strategy of using RT Connect to quickly obtain a feasible path and heuristic path shortening to refine it. On the right plot, we see that this combination discovers initial feasible paths more quickly than LazySP, although both PSMP and POMP can effectively leverage the finite set posterior and beat both baselines. On the left plot, we can also see the initial paths discovered by PSMP are much shorter than those discovered by POMP or the RT and path shortening combination. In conclusion, anytime algorithms should rapidly discover progressively shorter paths. We formalize this intuitive objective as minimizing Bayesian regret. PSMP achieves sublinear Bayesian regret, which implies asymptotic optimality while demanding good intermediate performance. We hope that this new connection will open the door to further regret analysis of anytime algorithms. Thank you very much for watching this video, and I look forward to your questions.